Plato and even like Kepler, who thought that the reason planets moved was because they had like some essence in them that helped them to move. They couldn't move.
Alright, let's start. It's funny how you guys are discussing philosophy. That you're discussing your philosophy on philosophy. But these philosophers are so like, and you guys are literally having a philosophical discussion about philosophy. Anyway, let's move on. How was the test?
Good.
Pretty good?
Yeah.
Make them harder.
No.
No.
Yeah, that's what I like.
No.
Okay.
I was short on time.
Yeah.
Make it shorter.
Did you guys actually get to the bonus problems?
No.
You didn't get to the bonus
No.
problems?
No.
Okay.
It
But
was
the,
hardly time to
Yeah.
go over the questions on the main
Okay.
exam.
but you felt okay with it.
Yes.
Yeah.
Okay, well we'll see.
Fair.
That's something to keep in mind. So we're not going to do a lot today. We're really only going to do one thing because my class this morning was in really bad shape. They had a 10 midterm right before the class. So I decided to speak very slowly. And so we really only spoke about one topic. We're going to apply derivatives. We're going to look at limits again. We're going to apply derivatives here. So the one topic I want to talk about today is the idea of an indeterminate form. And basically, one of the main ways we know how to do it, called L'Hopital. So L'Hopital is this French dude that sponsored this theorem. I think his name, if you actually write it out in English without that weird character that we don't have in English, it will literally spell out hospital. And I think L'Hopital probably means hospital in French. But, so yeah, so back in the day, my kids used to say when I have to, so how do we solve this problem? Take it to the hospital, you know? Okay, so there's a little humor there. But yeah, L'Hopital rules allows us to deal with certain indeterminate forms, and it is a process that you apply to limits, and it is actually an application of derivatives applied to limits. So we can actually use derivatives to figure out limits in certain cases, and that's basically all we're going to talk about today. So first, an indeterminate form, as its name suggests, is just a form that you can't really determine what it is right off the bat or at face value, because it has competing ideas where you're like, well, the answer is, I feel like it should be this, but I also have a good argument for it to be that. So it's kind of like I don't really know how I'm going to apply this. I have competing mathematical thoughts and I don't know how to deal with them. So these are limit forms. That we can't be determined at face value. Because of competing ideas. So let me give you some of the examples of indeterminate forms, right? And again, these, remember, it's in the context of limits, okay? So one indeterminate form is infinity raised to the 0, right? Now that, if a limit approaches an expression that behaves like this, it's kind of weird, because on one hand, if the base is infinity, it should be infinity, but on the other hand, if I raise anything to the 0, shouldn't it be 1? 1 and infinity are obviously kind of different. What would that actually be? It turns out that this expression can lead to a whole range of answers. And any of these things that I'm writing down, the answer could be quite literally anything depending on the situation. Another one is 1 to infinity. On one hand, raising something to an infinite power, I feel like it should go up to infinity. But on the other hand, if the base is 1, shouldn't the answer be 1? Things like 0 times infinity is another one. On one hand, multiplying infinity should make something infinity, but multiplying by 0 should make it 0. You know, who's going to win here? Right? So that, another one, infinity minus infinity. Now, some of you might not see like there's an issue here, but for those of you who kind of know the idea that one infinity can be bigger than another one, will know that this can have some conflicts here, right? Because now it's like, which one's the bigger one? Are they the same kind of infinity? Maybe it's 0, but maybe this one's slightly bigger than that, or maybe this one's slightly bigger than, right? There are issues here. Another kind of indeterminate form is 0 divided by 0. And remember, this is concepts of limits. So I'm not saying we're actually divided by 0. I'm saying the limit is approaching a quantity that has this kind of behavior. Both the numerator and denominator are getting small at the same time. And what would we do with that? Conversely, what if both the numerator and denominator are getting larger and larger at the same time? So these are what we call the indeterminate forms, because they have these competing ideas where really at face value you can't really say, because you have really good arguments for one way or the other. And so we want to be able to deal with these forms because they show up actually pretty often. One thing that provides a ray of hope is what we call L'Hopital's rule. L'Hopital's rule says these two guys, we actually know how to deal with them. Okay? So it turns out that these two particular indeterminate forms are more convenient in some sense than the other one because we actually specifically know a rule that can deal with these guys in a lot of cases. And that leads to what we call L'Hopital's rule. L'Hopital's rule states, consider the limit of one function divided by another function. Now, this is the important part. If this limit approaches the forms 0 over 0 or infinity over infinity, and of course here it can be plus or minus, right? If we're approaching one of these two specific indeterminate forms, then it turns out that the original limit that I wanted to compute will be equal to another limit that might be easier to compute. So that particular limit will be the following. Take the derivative of the numerator and the derivative of the denominator. It turns out as far as the limit is concerned, the ratio at which the functions are changing is going to be equal to the ratio at which the derivatives are changing in the limit, right? So it turns out that this limit can be computed by figuring out that limit. And a lot of times, this limit will be easier to compute, right? You can imagine that if this one is an x squared, that one was only a 2x, right? 2x is a simpler function in some sense than an x squared. And that's just a very lucky coincidence, but it turns out to be true. And this idea, this is a theorem called L'Hopital's rule. If our limit approaches one of these two values, then these two will always give you the same value in the limit. And so we can use derivatives to get a different limit, which hopefully this one is not going to be indeterminate. Hopefully this one gives us a form that we can know exactly what it is. And in theory, we can actually keep applying this process. So if this limit now gives us one of those again, we can apply L'Hopital's again and again and again. And hopefully the idea is eventually this process will end up with a limit that we actually know how to deal with. Let's do a very simple brain dead example, just to give you at least anecdotally that this will work. And my first few examples are going to be like that, so maybe let me just throw this in as one of the examples. So these first three, you kind of know what the answer should be anyway, but we're just going to verify them using L'Hopital's rule. So the first one is the limit as x approaches 0 of sine x over x. And let's continue with the other ones. x, c, limit as x approaches infinity, and then x over x, limit as x approaches a 0 from the right, x ln x. Limit to 0 from the right of x raised to the x power. I have a lot of examples here. I don't want to do all of them. Maybe try this one. Limit as x approaches infinity. 1 plus 1 of x raised to x. One from the right. So infinity into x minus x. Limit as x approaches infinity. One from the right. Right. So we're going to do those examples and then we get out of here. Okay. So the first one you should know by heart. That's 1, right? That was a special trig limit. Let's see how L'Hopital's rule would have dealt with this. So let's say you're in the twilight zone. The test anxiety is getting to you and you forgot what that was. Very inconvenient time. Turns out that if you remember L'Hopital's rule, you can actually rediscover this with a lot less work than it was derived in the first place. I mean, we didn't derive it, but if you read through the textbook how this was derived, geometrical argument takes forever. It would take you a really long time to rediscover what that is. However, with L'Hopital's rule, it's actually not so bad. If you look at A, and you just look at what this limit is, how this limit is behaving, you'd realize that if my x approaches 0, the sign of x would approach what? It would also approach 0, because sign of 0 is 0. Similar in the denominator, x approaching 0 means the denominator will approach 0. So notice that this has a form of 0 over 0, right? Which is indeterminate. Can't divide by 0. What does that even mean? Okay. So that's the form. So what you can do is you can apply L'Hopital's rule. It says if something approaches this form or that form, these two forms specifically, then this limit can be computed by doing that limit. So what we can do here is apply L'Hopital's rule, and we usually indicate this by doing something like that over the equal sign, so that to indicate to the reader I'm thinking about L'Hopital's rule here. This is going to be equal to this limit. Take the derivative of the top, which is cosine. Take the derivative of the bottom, and that's 1. And it turns out that because this approaches that indeterminate form, this limit is actually going to be equal to that limit. But what is this limit? Well, that approaches cosine of 0. At this point, I can just plug in x equals 0 with no problem. Cosine of 0 is 1. So that's a nice little verification. Yeah, so that was a very, again, we know what this is, and it should be no surprise to you that the answer is 1, but here's a way that I'm demonstrating L'Hopital's rule, right? So whenever we have a 0 over 0 or an infinity over infinity, this rule will apply. It does not apply to the other indeterminate forms. It's important for you to know that. But the idea is sometimes the other indeterminate forms you can kind of finagle and force them into being one of these forms. And some of these examples you'll see how we can do that. Some techniques for doing that. The next two limits you should also be able to talk about what the answer would look like. I mean, what about B? What do you think the answer should be?
I have a question.
Yes.
So the top and bottom answer shouldn't have to be same, so it can be negative infinity and over positive infinity?
Yeah. Just once one is going from, both are getting bigger and bigger and bigger. What would you think this is going to? Yeah?
Infinity.
Why?
because the top is like really big than the bottom.
Right, so we looked at the behavior of functions way back when, and we know that functions that look like this that are polynomials compared to functions that look like this that are exponentials are a lot bigger when you're going off to infinity. So I expect here the numerator to overwhelm the denominator, and so this will be infinity. And so, but one way we can get to that idea, even if you forgot about that process, is you would notice that as x is going to infinity, e to the x is going to infinity, right? This graph looks like that. Similarly, as x is going to infinity, x goes to infinity. So this has the form infinity over infinity. I can figure out what that is by applying L'Hopital's rule. So that limit will be equal to the limit if I differentiate the top over differentiating the bottom. Right? So it's important that you know I'm not applying the quotient rule. I'm differentiating the numerator and the denominator independently. Now, this is just the limit of e to the x as x approaches infinity, which should be clear that infinity is the answer here, which makes sense. That falls in line with our intuition. Right, so there are a lot of cases where we would have, even if we don't have a computational sense of doing it, we do have some sort of intuition for what the answer should be. L'Hopital's rule allows us to actually put a computational bend on our intuition. Similarly, I would expect that guy to approach 0. Why? It's a logarithm compared to a polynomial. The polynomials are much bigger. So I expect the denominator to overwhelm the numerator. So I have a fraction where the top is really, really small and the bottom is really, really big. And so you can check the form here. ln of x looks like that, so it's increasing, so it'll move to infinity as x goes to infinity. X itself will move to infinity as x goes to infinity. And so this is infinity over infinity. We can apply L'Hopital's rule. Differentiate the top, 1 over x. Differentiate the bottom, it's just 1. Well, that's just the limit as x approaches infinity of 1 over x. That one is not indeterminate. It is clear what that is, 1 over x. We know the graph looks like this on the right side. That approaches 0. So those are the easy examples because we actually know enough otherwise to figure out what these guys are. The other ones, though, are a little bit more challenging. So let's look at the first non-trivial example, this guy. As x approaches 0 from the right of the function x ln x. Now, if you start to look at the form that that guy is approaching, what would that be? What would you just say the type of form this is approaching?
Negative infinity? Oh, the form?
Yeah. What would x do? What would x approach? 0. What would the ln approach? Minus infinity. Right? So this is a 0 times infinity form here. This is indeterminate, right? On one hand I'm multiplying by 0, on the other hand I'm multiplying by infinity. That's strange. Who's going to win, and what would that value be? So this is a multiplication, okay, of 0 times infinity, right? Because my x is going to 0, and my ln is going to negative infinity, and so we have 0 times infinity. So that is an indeterminate form. However, it's important for you to note, L'Hopital's rule does not apply to this form. L'Hopital's rule only applies to 0 over 0 or infinity over infinity. However, we're great at algebra, and so it turns out if we have a multiplication of this form, we can rewrite this algebraically to have one of the other forms in the following way, for example. I can take this x and I can think of it as 1 over 1 over x. Now, based on what we know about fractions, this is actually the same as that, right? Because if you take the denominator, the fraction in the bottom, keep, change, flip, is the same as multiplying by x, right? Multiplying by x is the same as dividing by 1 over x, as long as your x isn't 0, okay? Now, remember, the limit doesn't actually care about being 0, so we're kind of safe in doing this manipulation. So I can rewrite it like that. And now, if I check that form, ln we know goes to negative infinity. Now look at 1 over x. As x is approaching 0 from the right side, what does 1 over x do? No. Positive infinity, right? 1 over x looks like this and that. So as you approach 0 from the right side, it goes up. It goes to positive infinity. So this is an indeterminate form of 0 times infinity. Don't know what the hell that is. However, I can rewrite this using what I know about fractions, rewrite it in this form, and that gives me an infinity over infinity form, which means now L'Hopital's rule is an option. It wasn't before. So now what I can do is take it to the hospital. Kids say that on this thing. So this limit will be exactly the same as a new limit that I can construct by taking the derivative of the numerator and denominator individually. What's the derivative of ln x? 1 over x. And the derivative of 1 over x? Minus 1 over x squared. We already did the test today. We don't have to know this anymore. Like, I don't have to remember this until like 2 months from now. Okay. Now that, I would first simplify that a little bit. So again, we apply the keep, change, flip thing, and this will actually simplify to minus x. And now when you realize, now when you find that limit, that's not indeterminate at all, right? Minus x as x approaches 0 is 0. And again, something is to be said about intuition here. Again, we have a polynomial and a logarithm competing. We know the polynomial is heading for 0 and the logarithm is heading for infinity. However, the polynomial is going to get to 0 a lot faster than the log is going to get to infinity. And so by the time the log starts getting really big, the x has already done the damage, and the 0 will actually win in this case. Alright, so the derivative of the limit of that is actually 0. Now, here's a function that we looked at last time. We learned how to differentiate this last time using log differentiation or one of the other techniques. Now let's actually look at a particular limit. Now, as x is approaching 0 from the right, what is the form that this guy is taking? To the 0, which is another indeterminate form. It is not a form on which we can use L'Hopital's rule, though. However, that is distinctly different from this scenario, where here I could just kind of flip one of the guys and move it. But how do you actually deal with the x power? That is a little bit more complicated. Now, one of the things that I do want you to learn from this course is just some general strategies of how you want to approach something. Whenever a power is a problem, what should be one of the first things you think about? Logs. Logs should be the first thing you think about. If you end up in a situation where a power is a problem, a logarithm should be one of the first things to come to mind. So now we have to think, is there a way to get a logarithm in play? Well, the answer is yes. We actually did the same thing when we tried to figure out the derivative of that. we sort of rewrote it in a way that a log gets involved. So that is what I would do here. So here, we can't get away with a simple algebra trick. We have to get away with a little bit more sophisticated trick, in the sense that I know I can rewrite x to the x as e to the ln of x to the x. Now at first you might think, well, that makes things a little bit more complicated. But we know two things that happen here. The first thing is that this guy allows me to take that x power and bring it down. So the power is going to become that. The second fact we know is that limits pass through continuous values, right? So the limit in front of an e to the x, I can take the limit and move it up to the power. So in other words, this limit is exactly equal to that limit. And so now, all we have to do is focus on the power. Right? So now when you're focusing on the power, you realize, well, that's an example actually you did before. You would now rewrite and apply L'Hopital's rule in the power. And so similarly, we would get here, last time we just looked at this, the answer was actually 0. So this is equal to e to the 0, which is 1. And that comes from applying L'Hopital's rule in the power, as in the previous example. So these are some general principles, again, that we're taking advantage of. If a power is an issue, use a logarithm. This is an easy way to get a logarithm in play. You could also do, maybe I'll show you the other way, just to kind of reinforce some ideas from last time. If you happen to like the logarithmic differentiation way of doing things, that will also apply here. So we could do something like alternatively. Right. When I give you an alternative, just pick whichever one you like more and forget the other way. So some people might like doing it this way. Alternatively, what you can do is you can set y equals to the limit that you want to find. Then you can log both sides. Then you can use the property that limits pass through continuous functions. We know logarithms are continuous functions. So I can slide this limit out. And so then this just becomes the limit as x approaches 0 of x ln x. Which again, going through the same process as in the previous example, we realize that this actually gave us 0. Now, the thing you have to remember when doing this method is that the answer you get at this point is actually equal to the log of the answer you want. So this tells you that log of y is 0. So this means what you would do is you'd raise both sides to the e and ultimately end up with y equals 1 as the answer. So that limit is 1. Either way is valid. Don't particularly have a recommendation for one way or the other. Just pick whichever way you have a preference for. Yeah?
Can you go over to
This one? So the goal was to find this, this limit, which is that. So you set y equals that. You can log both sides. Log is a continuous function, so I can slide the limit inside and outside of the log. So that gives me this. Right? Now this allows me to bring this power down. So we end up with this, but we already know how to deal with that. We did that in example. So you'll go through all that calculation, you'll end up here. Now, what you have to remember is that that 0 represents the log of the y. right? You ln both sides in order to get to this point, which means what you've proven by going here is that the log of y is equal to 0. And so, but y is what we wanted. So you'll have to solve for y by eing both sides. And that will be 1. Now, rewriting it here already puts the e in play, so I never have to remember to e both sides. But if you like setting it out this way, you'd have to remember at the end, oh yeah, I logged both sides to get to this answer, so I have to undo the log that I threw in there to get to the final answer. Let's look at f. What do you guys copy this one? So f is interesting for several reasons. If you look at how f is behaving as a form, you'll notice that as x goes to infinity, 1 over x is approaching 0, which means that the base here is getting closer to the number 1. Now as x is approaching infinity, the power is x, obviously the power is approaching infinity, so this approaches 1 to the infinity. And so now on one hand you're like, well, the base is 1, shouldn't the answer be 1? On the other hand, we're raising to the infinite power, shouldn't it be infinity? The actual answer is that neither of these are true. What is this limit? Yeah, that's e. We actually know what this answer is. The answer is actually 2.718, right? A random number. Right, which you can't really, who would have guessed that if you just looked at this form? Who would have guessed, oh, the answer is E? But we know the answer is E. Okay? So this is what I'm trying to emphasize with you about indeterminate forms. The form does not indicate to you whatsoever what the answer might look like, right? You have to really deal with these forms very carefully, right? That's why they're indeterminate. The answer can be very surprising. Okay? So we know this should give us E as the answer, but let's actually see how you would get to something like E. So again, one of the things that make this difficult to deal with is the fact that there's an x power here. So what I would try to do is do the same thing I did before. Let's rewrite this so that the power becomes a non-issue. So what I would do is rewrite this as e to the ln of that guy. Which makes this example pretty meta if you think about it. Kind of like discussing the philosophy of philosophy. We're using E to find itself. It's very interesting. The answer is going to be E, and we're actually using E to figure out that the answer was E. But that's one way we can actually do this. So again, what I would do is now we can bring this power down in front. And now, because limits pass through continuous functions, it means I can consider this to be e raised to the limit of this guy. And so now my focus is strictly on the power, right? There's a limit in the power. Let's actually put our focus there. Now, what's actually happening in the power? What's the form of this limit? this guy's approaching infinity times this guy's approaching log of 1, which is 0. So this is an infinity times 0 in the power. It's an indeterminate form. It's not a form that L'Hopital's rule can deal with, so we have to kind of do some finagling here. What's the finagling you would do? Yeah?
ln of 1 plus 1 over x over 1 over x.
Right, so again, do that same thing. X is the same as 1 over x. So I would rewrite this as ln of 1 plus 1 over x over 1 over x. So using a little algebra there. And now again, I check what's the indeterminate form now. Well, as x approaches infinity, this approaches 1, that's log of 1, that approaches 0. And as x approaches infinity, 1 over x also approaches 0. So this now gives me a 0 over 0 form, and that says L'Hopital's rule is now an option. So at this point, I'm going to apply L'Hopital's rule to this problem. So now, in the power, I'm going to take the derivative of the top and divide by the derivative of the bottom. So what is the derivative of this guy? Yeah?
Negative 1 over x squared over 1 plus 1 over x.
Right. Negative 1 over x squared times 1 over 1 plus 1 over x. What about the bottom?
Negative 1 over x squared.
It's negative 1 over x squared. In other words, now these guys would cancel. And so this looks like back over here. Now this would look like e to the limit of 1 over 1 plus 1 over x. Now is that limit something we can deal with? What is that? That's actually just 1. This is e to the 1. So the answer is e. Very interesting result. 1 to the infinity in this case is e. Right, I could flip the script here a little bit. I could also do something, I'm not going to do it, but just to show you, I could have done something like this. And that answer would also be e. Right? Because that still is approaching 1 to the infinity. You can even try to redo this problem in that variation. It will also give you e as the answer. So that was an interesting example, I think. Let's move on to G. So again, letting x approach infinity, you'll realize what this guy is going towards as a form. E to the x will approach infinity as x approaches infinity, and x itself will approach infinity as x approaches infinity. So here I have an infinity minus infinity, indeterminate form. Now I do have some sort of intuition here, because my e to the x infinity should be much larger than the x infinity in terms of rates. And so probably I'm thinking that the first infinity is going to win and be bigger. And so the second infinity is kind of like nothing. And so I expect the answer to be infinity. But let's actually do this with a little more careful calculation. So here we have a subtraction. So it's not a matter of being able to, what we did here, if we had a multiplication, we can move one of these products underneath by just putting 1 over it. Here we don't really have that option. We have a subtraction. And of course, logging the subtraction won't make a difference because I would need a log on each part in order to create a division. So logs won't really be what we do here. But the process in which we think about this would be to first turn the subtraction into a multiplication, and then, if need be, turn that multiplication into a division. And how do you turn a sum into a multiplication? What process do you know does that? The what?
Logs.
Logs do what? Turn a sum into a division?
Multiplication.
Yeah, but it's very important that you realize how that actually works, right? It's if you have log of right? So the log rule wouldn't really apply here because the log rule requires that the log is on each individual part. That wouldn't be the case here. And even if I took the log of this thing, like if I take the log of something like this, logs do not distribute across sums. So I can never actually get to this point to apply that rule. Right? So that would be probably something you would think about, but you'll quickly abandon that idea because we actually need the logs on individual parts to get that to work. There's something more elementary. How does a sum become a product?
Can you like multiply and divide by the conjugate? I mean, that would complicate.
There's no real conjugate here, at least not in any sense. The answer is factoring. Factor. Something we learned in algebra class. Factoring is a way to go from an expanded form to a product form. That's the whole point of factoring, right? If you see like x squared plus 2x plus 1, factoring brings it to this position. Right? Factoring is a process for going from an expanded form to a product form. Expanding is the process from going from a product form to a sum form. So here I have a sum of things. To get it to be a product, factoring is the first thing I would think about. Now, it doesn't really matter who you factor out here, but let's factor out the x. Now, if I factor out an x, what is going to be left over inside? Yeah?
3x over x minus 1. 3 to the x, right?
3 to the x? I think
oh my god, I just had like an aneurysm.
Yeah.
EX
over
x over x.
Yeah,
Oh
E3, they sound very similar. Yeah. E to the x over x minus 1. Because when we're factoring, what we're really doing is we're kind of multiplying and dividing by the same thing and letting the denominator go inside the parentheses. Right? So that's what we have. Now this puts it in a product form. And so now we can sort of talk about, okay, in this product, what is the actual form that we're approaching? Well, x is approaching infinity. What about the inside? Well, inside, we have a minus 1 here. What about this guy? What is this guy approaching? Right. But we actually even dealt with that guy before. What did we get that this ratio approaches? It approaches infinity, right? I have an exponential on top of a polynomial. Now, so this approaches infinity minus 1. Infinity minus 1, still infinity, right? So this actually approaches infinity times infinity. Now, is that indeterminate? The answer is no, that's actually not indeterminate. We know exactly what that is. I take a huge number, multiply by a huge number. There's no argument here. The result is a huge number. Right? A big number times a big number is a big number, right? That's not indeterminate. There's no competing ideas here. This actually becomes infinity. Right, so that one was just kind of a fake out. This is actually not indeterminate. Infinity times infinity is considered to be infinity. Right? infinity minus infinity, that's kind of nuanced because it depends on which one is bigger. Same thing, infinity divided by infinity, that's kind of nuanced because again, it depends which one is bigger. The answer can change depending on who is this. But in terms of sizes, it doesn't matter who is the bigger infinity here. Infinity is the only logical answer.
What about infinity plus infinity? It's still infinity.
Yeah, infinity plus infinity. If you have a positive infinity plus another positive infinity, it's a positive infinity. Right? The subtraction makes the difference. So that's actually not indeterminate. That was just factoring. What about this guy, H? So we look at that guy. Well, what is the form of this? As x approaches 1 from the right, what does log do? Yeah?
This is 0.
It approaches 0. So it approaches 0 from the right. Right, so it's approaching 0 with a positive charge. What about this guy? As x approaches 1 from the right, this guy approaches what? Hmm? One over 0 with a slight positive charge again, right? Because my x is slightly bigger than 1, and I'm subtracting 1, so I'm left over with a very small positive number. Conversely, you could recognize that 1 over x minus 1 is just a shifted 1 over x graph, and as you approach 1 from the right, it's going off to infinity. This actually gives you infinity minus infinity. So, somewhat similar to the last problem, except here, I probably wouldn't jump into the factoring route because the way things are, this is actually a subtraction of fractions. So what I would do is probably just combine the fractions. That would give me a division relationship right away. So the move I would make for a problem like this is to actually combine the fractions first, then see what happens. So to add these two fractions, this would be x minus 1 minus ln x all over x minus 1 times ln x. So now we have a division. Let's check what this approaches. Well, as x approaches 1, this becomes 1 minus 1, which is 0. As x approaches 1, ln of x will be log of 1, which is also 0, so the numerator goes to 0. Under here, as x approaches 1, this part goes to 0. Also, this part goes to 0, so the denominator behaves like 0 times 0. So it's over 0. So here we have a prime candidate for L'Hopital's rule. By combining the fractions, I immediately get that L'Hopital's rule applies. So what I'm going to do is take it to the hospital. Differentiating the top, derivative of x is 1, derivative of 1 is 0, derivative of this guy is going to be 1 over x. Differentiating the bottom is a little bit more nuanced. That requires some product rule here. Still a thing, always will be a thing. All the rules are always applicable in the right circumstances. So differentiate this, leave that alone, differentiate this, leave that alone, add these together. Derivative of this is 1, multiply by ln x, plus leave the first one, and multiply by the derivative of ln x, which is 1 over x, so that becomes that guy. Now, if things are a little bit complicated after applying L'Hopital's rule, I would simplify before deciding whether I want to do it again. So simplify this fraction by multiplying by x over x. See what we have here. So the top will give me x minus 1. And the bottom would be x ln x plus x minus 1. And now I would check again. What is that form? As x approaches 1, the top approaches 0. As x approaches 1, the bottom again approaches 0. What do? Well, apply L'Hopital's again. Back in the hospital. So there's nothing about L'Hopital's rule that says you only have to do it once. Sometimes you can end up in a situation where applying it multiple times will be the way to go. So we would apply it again. Derivative of the top in this case is 1. The derivative of the bottom, this part is product rule, ln x plus 1. This part is 1. So this will be what? Yep.
1/2.
Just 1/2. That's actually a half. So we will stop there. And on Friday we will continue with inverse functions. Not in detail, but